Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediate. In the previous class, I talked about carbene, I talked about various reaction about carbene, I talked about the addition reaction, insertion reaction, and in the today's class, my plan is to talk about several other reaction using carbene. So I'm going to start with the generation of carbonyl halide, then I'm going to talk about the generation of sulfonium halide. Then I am going to talk about in heterocyclic carbene, and briefly going to talk about Graf's catalyst, because as you can see the metal carbene is not part of this course, and then also briefly talk about the metathesis reaction as well. And then at the end I am going to talk about some of the questions from the exams, from the previous exams. Okay. So first thing I am going to talk about that the generation of this halide species. So what is happening, I think so, generation of carbonyl halide. So we have learned in the previous class that from the diazo compound, once you take the transition metal like the rhodium tetraacetate or copper, you have seen that it generates this metal based carbene species. Okay. So it actually how it is forming from here to here, I think I already told about this, that it going to form some sort of a species like this. Okay, so it has a metal, it has a so then what is going to happen, then there will be N2 going to get out from here, which will end up generating this type of species. So we call this species as a carbenoid. So this species is carbenoid, I think I have explained in the last class, and these are called transition metal based carbene. So what is going to happen now, the oxygen lone pair is going to attack here, and then it is going to generate some sort of a halide species called carbonyl halide. Okay. In the carbonyl halide, if you see in a lot of places people don't write this MLN here, people just write like this, just a plus and a minus. But if you see in the literature, this metal is actually attached in this stage. After once the reaction was done, then the metal is get out from here and get back to the catalytic cycle. So once it is forming this particular halide, now you can see this has a 1,3 dipole type of system, so it can participate in a cycloaddition reaction with olefin. Okay, so it will be a 3+2 dipolar cycloaddition going to form this type of 5-member ring. It can also participate in this epoxidation reaction. If you don't have olefin here, it can attack here and then form a corresponding epoxide. Okay. Everything actually given here, very similar thing is drawn here, that from this diazo compound it is forming this transition metal based carbene, and then from there it is the carbonyl group is attacking, forming this halide which can now participate. So here we are showing some some sort of a cycloaddition using the alene. Okay. So now I am going to show you some example of it. You can see this alpha keto diazo compounds in presence of rhodium tetraacetate. It can form this corresponding metal based carbene which can get attacked from this carbonyl oxygen lone pair, which end up generating this 1,3 dipole, which can participate in a 1,3 dipolar cycloaddition in a intramolecular fashion. So you can see these two fragment can come closer to form this corresponding product here. There is another example here. Here also you can see there is in this alpha keto diazo compounds form this corresponding the carbene, and then this carbene is getting attacked with the oxygen lone pair, formation of this 1,3 dipole, and then in a reaction with this alkyne with 2 electron withdrawing group to form this corresponding product here. So then there is another example here. I think this example is interesting, because here first thing is what is happening, again they are starting from this corresponding alpha keto diazo compound formation of this rhodium based carbene, which is now getting attacked with this oxygen lone pair of this O-methyl group here. Then from this particular transition what is happening, you can see generation of this negative charge here, which is allowing a 2,3 sigma-atomic rearrangement. So here instead of a cycloaddition, once it is attacking here, you know that it is going to generate a negative charge. So now this negative charge can attack here, and then its double bond can move here, and it can cleave this carbon oxygen bond. It can cleave this particular bond. So via 2,3 sigma-atomic rearrangement, it is going to form this particular product. There is another example here using copper instead of the rhodium. I think I have already discussed that also, the generation of the corresponding carbene transition metal based carbene species in the previous class. Here also what is happening, at the beginning there will be a generation of the metal based carbene which is getting attacked with the oxygen lone pair here to generate this elite species which will participate in this 2,3 sigmatopic rearrangement, okay, and then the cleavage of this carbon oxygen bond will generate this compound. Now I am going to talk about sulfonium elite. So what is going to happen here? Again you can see using this type of diazo compound here, using the the rhodium tetraacetate, it can form the corresponding the carbene species which is going to attack with this thiophene. The sulfur has a lone pair here which is going to get attacked here, and then it is going to form some sort of elite species here. Now it can once it is forming the elite species, now it can do several different transformations. Some of the example is given here from starting from this particular diazo compound, it is forming this this compound. Now once you have electron withdrawing group here, the negative charge moved in this position, which will allowing this 2,3 sigmatopic rearrangement. The negative charge is attacking here, this carbon sulfur bond is getting clipped. Once the carbon sulfur bond is getting clipped, now you can able to get to this type of intermediate which happening here. There is a 1,3 hydride shift happening, so this is shifting here to form this corresponding product. Okay. So these are very interesting reaction. You can see starting from this diazo and then in the transition metal, and then using some sort of carbonyl compounds or a corresponding sulfur analog, you can able to do this type of cool rearrangement. I think Professor Padua group actually developed this type of chemistry, and there are lot of development in this area. So there are a lot of different cycloaddition reaction done with this type of elites. So now I am going to move to this N heterocyclic carbene. You have seen at the beginning when I was talking about the isolation of a stable carbene, I think I talked about the Arduino carbene, which was the one which was got isolated and it can be stored. So that was the things I was talking at the beginning, and if you remember I was talking about that the NHC have two adventile groups so that the NHC cannot able to dimerize. So now I am going to talk about this N heterocyclic carbene. Of course, I cannot able to spend too much time, but just briefly talk about how they form and what are the different types and how these N heterocyclic carbenes are stable. Okay. So you can see in the first example, it is the deprotonation of imidazolium cation. So you are generating this imidazolium cation by the alkylation, and then what is happening now, it is the abstraction of this carbon hydrogen. Okay. So once this deprotonation is happening, that is actually generating this N heterocyclic carbene. Okay. So one of the important fact about the N heterocyclic carbene that it is sigma electron withdrawing and pi electron donating. So you can see, I think I have already going to explain the same thing in the next slide through the molecular orbital. Okay. So there are various different type of bulky group you can see. So those bulky groups kind of stop, it is going for making as a dimer. So there are, you can use this 2,4,6 trimethyl. It could be a 2 and 6% the isopropyl group here. Okay, so there are lot of variation in this type of NHC carbene. I have tried to put some of the variation here. You can see I already talked about this one at the beginning. Now you can see it could be a imidazolidine, that means you don't have this double bond here. And then there are several variation. Instead of the nitrogen, it could be nitrogen in one side, then the other side will have oxygen or sulfur. So that could be thiazolidine or oxazolidine. And then there are other variation of carbon variation here also. And then there are some chiral NHCs. So chiral NHCs are also very important compounds, is used for organic as a organocatalyst for various different transformations. Then there are also 6-7 member NHCs. Okay. Again, I think there are good lectures on this particular topic. So I am not going to cover the reactions of the NHC. I am just going to briefly talk about their structure, and then the question is why they are so stable. So here I am going to make a summary of this N heterocyclic carbene, that so they have these important things here which I was trying to tell you from the first slide, that there is a pi electron donating and a sigma electron withdrawing. So these are the two important effects which makes these N heterocyclic carbene stable. So one of the thing is, what is the sigma electron happening? Because the sigma electron withdrawing happening, you can see here this arrow is given here. So it is getting the sigma electron is getting pulled, and at the same time there is this the non-bonding electron from the nitrogen is getting transferred to the empty p orbital of the carbene. Okay. So that is a pi electron donation. Okay. So this is the two effect. So I think I have explained here. So the inductively sigma electron withdrawing and then the pi electron donating. Okay. Again, I think there are different type of backbone. As I shown you in the previous slide, you have seen there are several different backbones for. So the kinetic stabilization from the steric bulk, as I mentioned. So that is one important factor. The kinetic stabilization comes from the steric bulk. It prevents the dimerization, which I was trying to tell you from the first slide onwards. That it actually prevents the dimerization. That's why these bulky groups are important. Okay. And then of course these are potential for asymmetric induction, as I going to show you in the last slide. There are a lot of chiral NAC which was regularly used for a lot of different asymmetric transformations. So now I just going to show you just some example of the Graf's metathesis in reaction and generation of the ruthenium, the carbene complex. Again some textbook call this as a carbenoid, but I think it is better to call this type of complex as a ruthenium carbene complex. So what is happening? First thing, this generation of this stable complex, how this is happening again from this corresponding diazo compound using this the ruthenium catalyst and tricyclohexyl phosphine. And once this stable complex is formed, this complex can be used for various different type of metathesis reaction. So there are several development in this catalyst. So I think I just now I talk about the first in the Graf's catalyst in 1995. After that the Hoveda group and the first the Hoveda Graf's catalyst was developed. You can see the skeleton is getting changed. Instead of this, you can see now there are different variation in the skeleton. In the second generation of the second Graf's catalyst, the NAC came into the play. Okay, so that is, as you have seen, the NACs are very good ligand for this type of reaction, and it is actually a very stable carbene, as I mentioned. And then it there are some third generation Graf's catalyst and more. We are going to briefly learn about that, what this type of catalysts are used for. So one of the important reaction is ring closing metathesis. Okay, and for this important discovery, and Graf's received a Nobel Prize on 2005 for this metathesis reaction. Okay. So here I can show you the general mechanism of the ring closing metathesis. You can see from this type of corresponding tangential metal based carbene, the ruthenium carbene species. First thing what is happening, a 2+2 cycloaddition. Once it is react with a olefin. So it taking this olefin, forming going for the 2+2 cycloaddition, forming this metallocyclobutane intermediate. That is a very important thing, that it formed this metallocyclobutane, and then after that what is happening, it lost the ethylene. So you can see it lost the ethylene, and then it is forming the alkylidene. It is forming this corresponding alkylidene, means again that the tangential metal based carbene species is getting formed, which is participating for another 2+2 cycloaddition to form again this type of the metallocyclobutane intermediate. From there again you can see it is the catalyst is getting back after eliminating this type of cyclohexene as a product. So this is happening. What is happening? It is actually forming a ring from these two terminal olefin. It is forming a ring. There is cross metathesis reaction. Instead of using a intramolecular version, if you have two different olefin and using this type of ruthenium catalyst, you can able to get a cross metathesis product. So what is happening? You can see from this part, if you just cleave here, then there is a CH2 and there is this CH2. That means a ethylene which is actually get out from here to get to this corresponding product. Again mechanistically is going to be very similar. It takes this olefin and then first form the the cyclobutane, then the decomposition of the cyclobutane, the metallocyclobutane, then it is going to add with another olefin and then further going to form the corresponding product. Then there are other class of reaction like in-ion metathesis. Okay, so here what is happening? The reaction is happening with a alkyne. Okay, so that is the first thing. Again, I think the 2+2 forming this type of, now it is a metallocyclobutene intermediate. Then there is a reverse 2+2. So that means this cyclobutene is getting decomposed to form this type of. Once it is forming this, it is actually participating in another 2+2 here. Okay, so now you have some sort of a double bond. So it's with this type of metallocarbene, there is a double bond attached. So now it's a kind of a diene type structures which going to now participate in another 2+2 with another olefin. Now it is going to form this metallocyclobutane, and then again the reverse 2+2 going to give this the 1,3 diene compound, and this ruthenium catalyst is coming back to the catalytic cycle. Okay, So now I am going to talk about some example about this, the ring closing metathesis. Here you have seen that there is 2-terminal olefin here which is participating in the ring closing metathesis to form this compound. Okay. There is another example here, you can see again this 2-terminal olefin is participating in the ring closing metathesis to form some sort of a cyclopentene. There are some other class, as I said, I am not going to explain in a lot of the things, just for a part of a carbene things, I just try to explain some of the basics about it. But there are other lectures where you can able to see which is going to cover more depth about this type of metathesis reaction. There is in metathesis where I think if you have two different olefin that can also form one olefin, where you can see both the olefin where you will see the CH2 part will get out to make this corresponding olefin. Then there will be ene metathesis, it could be one ene and another is alkyne, again going to form this which I have already explained in the previous slide. Some more example about the ene metathesis reaction, where you can see there is a ene and then there is a ine which using the corresponding ruthenium catalyst going to form so you can see it is forming a cyclopentene with a olefin attached with it. Okay. Then there is another example here where you can see this is some sort of a cross metathesis happening again in place of the ruthenium catalyst to get to this corresponding the 1,3-diene product. So I talk about some of the things about the cross metathesis, and now I am going to talk about the previous year questions. So let us talk about some of the questions. So the first question is starting from this cis olefin once you use a singlet carbene, so what will be your product? Okay, I think I already talked about the singlet carbene reaction will be stereospecific. So it should be forming a stereospecific product, that means you should end up getting to the this particular answer will be your choice, not the other things, because you can see the other option, if you see this is the trans one which is not going to form, and it is not going to give you 50-50 mixtures, and neither this one. Okay. So here you can see that as I told, I think in the singlet carbene the reactions are very much stereospecific, that is why we end up getting to this product. This reaction goes by a concerted reaction. So if you go to my I think the second lecture about carbene, you will find that. Then there are some other question here. Once you take this olefin, go for this type of so you take the CH2Br2 in place of base to make to this corresponding the cyclopropane. So this will be addition of corresponding carbene, and then once you treat with the silver nitrate, what will be your product. Okay. So here what is happening? So in this question there are 4 answer is given. So let's think about the what will be A. The A will be of course the corresponding chloroform which is going for alpha eliminase so it will be CHBr3, not chloroform, sorry, it will be a bromoform which will in place of potassium terbutaoxide it will form the corresponding CBr2. Now it will form this corresponding cyclopropane, and then once you treat with silver nitrate, we have already learned once you treat with silver nitrate, you will cleave this one of the carbon bromine bond to generate a carbocation here. Once you have a carbocation, what is going to happen? Now it is going to, so this bond is going to get break to form another carbocation here. So you can see there will be another carbocation here which is going to get a protonated in place of water. It will end up making this corresponding allylic alcohol. So now we have to look for the answer. So I think in some of the cases they have given the CH2Br2. It is not going to be the choice. So you have to look for somewhere where you have CHBr3, and then you have to look for the structure of B. So the structure of B will be this one, correct? So you can see that will be your, so the answer D will be your right answer. So in the next question I am going to talk about a reaction here. You can see using the silver oxide and methanol, what is going to be your product. So let's try to understand. Once you have a silver oxide, I think we already talked about this, that it is going to form a ketene intermediate. Okay. So when I was talking about the Wolff rearrangement and the Arnold ester synthesis, if you remember that time I was talking about this, that you are going to generate a ketene intermediate in the presence of silver oxide and the H nu. Now once you have a ketene intermediate, now if you treat with the methanol, it is going to attack in this carbon to form this corresponding ester. Okay. So we look for a answer, because now the one important thing is this methyl stereochemistry will remain intact, because this we are not doing anything on this particular stereo center. So that's why you have to look for an answer where the methyl stereochemistry is going to remain answer. So that means this will be your right answer. Then there is an example, I think I already talked about the very similar example in the class where I talk about using indole. Here they have used the C2C3 dimethyl indole. So now if you take the condition of the CHCl3 aqueous NaOH, we know this is going to generate the CCl2 carbene. And once it's going to generate the CCl2 carbene, the next thing what is going to happen, it is going to go for addition with this double bond to make this corresponding cyclopropane. And now once you treat with a base, we have learned about that in this condition there will be a ring expansion going to happen. It is going to take this NH proton and it is going to come back and open up the cyclopropane ring and then eliminate one of the chlorine. That will generate, now you end up making a quinoline, which are substituted at the, you can see now there is the C3 position, you have a chlorine here. Okay. So now you can look for answer which is matches with this. So that means you have to find out. So of course in the question they might ask for both the things, means what carbene going to generate and what will be your product. So in that case you can see this is going to be right answer, because it is going to generate the dichlorocarbene and it is going to form the 3-chloro and then this corresponding the 2 and the 4-methyl quinoline. This is a very simple question. So I think it is, we have already discussed about the addition reaction of singlet and triplet. So in this question they are asking that if you start with this type of cis olefin, then if you take a singlet, what will be your product? If you take a triplet, what will be your product? Of course, we have learned that once you have a triplet, you end up getting a mixture, and once you have a singlet, the reaction will be stereospecific. Okay. So we have to see that in case of singlet, so these two methyl will be in the same site, but once you are triplet, that means I think we have to look for an answer where in case of singlet there will be single product, in case of triplet you have a cis and trans. So I think the option 1 will be correct. Okay, so you can see the singlet is this, and then in case of triplet you are getting a mixture. Then there is a question, I think I have already covered a very similar question in the class. So what is going to happen if you take this the rhodium tetraacetate with this compound, because this is a diazo compound. So it will first form a corresponding carbenoid, then it will going to form the rhodium carbene. And now what is going to happen, you can see in this particular scenario, once the rhodium carbene is going to form, it is actually going to participate in some sort of a insertion reaction. And the important part is, in this insertion reaction, which I am trying to explain here, it is going to form the corresponding trans product. I think I have already tried to explain you during the discussion. The important part is that once you try to draw this, because it is going to make some sort of a 5-member, so you have to understand that there will be two things happening here. So one is whatever groups are attached here. So that means if you have a 2 different position, you will try to avoid, suppose this is my CH which is going to get inserted, and this will be my CH3. So this will be my N propyl group, because at the end of the day you will see your the insertion happening from this hydrogen is getting inserted. So now the important part is that these two group here, that you have this COOET and this N propyl. Okay, so there will be a rhodium here, then there will be a CO. So now if you see that in this tangential, when it is going to abstract this CH, these two group can stay in the trans position to avoid the steric. That's why it will end up making to this particular product, not the other one. And then what is going to happen, if you treat with the NaBH3CN, sodium cyanoboroiodide, it is going to reduce the corresponding ketone, not the ester. I am sure you have learned this during the oxidation reaction. And now so this will be your product. Okay, you can end up seeing this product. So now you can look for this product here. So this is going to be option number B will be the right option. Okay. Then there is another example here. I think once you look into this, the tosyl hydrazine and n-butyl lithium, you can immediately think about a reaction I already covered, which is a Shapiro reaction. Okay, so we have already learned in the class that from the Shapiro reaction, what is going to happen, it is going to form the corresponding hydrazone. In-butyl lithium going to abstract this NH proton, then later it is going to abstract the alpha proton, and then there will be elimination of this tosyl, and the N2 generate this type of carbon ion which will be trapped with the DMF to make this corresponding aldehyde. So, the aldehyde will be the right answer. So, this is the another question here. I think I already talked about the Reimer-Tiemann reaction in the previous class. So, you can see, so this is a very important problem about Reimer-Tiemann reaction. Now, you can see in this substrate your para position have a methyl group. So, the ortho position there is no other group here. So, what is going to end up, and then what they are using after them, they are treating with H2 to NaOH. So, that is the important thing, that if you give H2 to NaOH, what is going to happen. So, let us try to understand the Reimer-Tiemann reaction. So, Reimer-Tiemann reaction going to give you this product which I already explained. So, this is a formylation of the phenol using this corresponding dichlorocarbene. So, now after that, once you treat H2 to NaOH, what is going to happen? It will participate in the Baeyer-Villiger oxidation. So, once the Baeyer-Villiger oxidation going to happen, so there are two groups, there is a phenyl and H. So, phenyl going to migrate. Then after the hydrolysis of this corresponding, so now the OH is going to attack here. Then after the hydrolysis, it is going to generate this corresponding phenol. Okay. So this will be the right answer, which will be the answer B here. So there is two different things actually merge. First thing is going to happen is the Reimer-Tiemann, and then the Baeyer-Villiger. I think I talked about both the things in the class. Again, I think these are the some of the problems from the previous exam, and I also suggest you to go through the different chapters of these books, and at the end of the chapter there are also a lot of problems, so you can also practice them. Okay. So thank you, and thank you for coming to the class, and I am going to see you guys in the next class. Thank you.